Morning, everybody. Congratulations being here on the last day of class before spring break. Takes commitment and panache and everything else. Notice the number on the chapter, right? 10, 16, and 17 in this unit. We'll go back to the others later. We're going to take what we learned about oscillating systems, things bouncing back and forth in that periodic motion, and we are going to apply them to waves. This is one of those topics where everybody knows kind of a lot about waves or think they know a lot about waves, and you do. Your intuition and your experience is going to be a good one. But if I ask the question, what is a wave?
Water frequency.
No, neither of those answers are correct. Okay, right? This is a wave, right? Not the kind of mechanical wave we're talking about. However, types of waves, or things that are waves, probably much easier. Name some things that are waves.
Water waves.
Water. Sound. Light.
Sine and cosine.
Signs, they're coming. Okay, right? So we know things that are waves. We can draw one. We can wiggle our arms and make, right? Okay, we could do the wave if we needed to. But what are they? I've got an answer for you. You're probably not going to like it. But we'll get into all of that, okay? So what I want to do to try to get into this idea of wave and wave motion is run a simulation. The reason we're going to use a simulation for this is that it can be really hard to see what's going on in a wave without slowing it down. And to make waves slow is really tricky to do, and to do it well and be able to see what's going on. So here's a simulation. Nowadays, everybody, if it's on the internet, it's real, right? But this one is actually based on real physics of traveling waves, okay? And so we have a wave on the screen, right? Based on what we learned last time, does this wave have amplitude? You can see it, right? You can just kind of wow, right? It's the height above the center line, isn't it? Okay. Is there frequency? Yeah, is there period? Yes. Okay. Notice what is generating this wave.
Stick.
It's a stick that's doing what? Going up and down attached to a circle, right? Why is the circle and the stick going up and down? What is this right here? It's a simple harmonic oscillator, isn't it? I mean, circles are simple harmonic oscillators. Sticks going up and down are simple harmonic oscillators. And if I bring out the dreaded laser pointer, okay, we could follow this peak along, right? But we can also take a look at just one of the dots. Let's take a look at this blue dot that's kind of right here in the middle right here. If you just watch that blue dot right there, okay, that blue dot right there, what's it doing? It's going up and down, right? Okay. Going up and down just like a spring or a simple harmonic oscillator. So, what is a wave? It's a series of connected simple harmonic oscillators. Told you wouldn't like the definition, right? Okay. But that's what it is. Now, are all parts of this wave doing exactly the same thing at exactly the same time? Yes, no? In other words, is the middle blue dot and the one over here doing it, are they at the exact same place at the exact same time? No, they're off a little bit, aren't they? If you look at all the different red dots that make up this wave, they're doing something differently than the one right next to them. We say that they are slightly out of phase from each other. If they were all in phase, they'd all be bouncing up and down with exactly the same time. All reaching amplitude at the same time, all reaching the equilibrium at the same time, so on and so forth. So a wave is different. A wave is something that evolves in time. It's going to make it difficult for us to kind of draw pictures of waves, because really what we need to be able to draw is this wave going places. Waves travel. And so we're going to define the speed of this wave. It's going to be the speed that one of those peaks is traveling across the screen. We got to define this thing called wavelength. The peak-to-peak distance. And don't worry, we'll write all this down. But I just want to show you a couple things here, right? Okay. We have a kind of low-frequency wave going on here, okay? And we can see this peak moving across the screen, okay? Going out the window, starts over here again, right? Moving my mouse about that fast. Okay, I'm going to change the frequency. What happened to the distance between the peaks? It got shorter, didn't it? Okay. But let's look at the speed of one of these peaks as it goes across the screen. It's not faster, is it? It's actually not slower. It's the same. So I'm going to bring the frequency back down. Okay. The peak of this one and the peak of that one are moving exactly the same speed. There's one lesson you need to learn that's going to carry you through into Physics 2B about waves. It's this. The speed of a wave depends on the material that it is traveling in. In physics, we use the word medium instead of material. The medium is the stuff that the wave is traveling through. And even though I'm about to write down some equations that look like they don't agree with this statement, you need to lock in on this idea. The speed of a wave depends only on the medium in which it is traveling. That's it. If we adjust the frequency or wavelength, doesn't change the speed. As long as the material doesn't change, as long as the medium doesn't change, we are golden. So let's get some of this down, right? Okay. So again, this is difficult to do, but when you draw a wave, you're either drawing a sine or cosine function. Doesn't really matter. Okay. But key parts of a wave, right? And it goes off either direction infinitely. Okay. Amplitude. Measured from the equilibrium point. And even though I didn't draw it very well, those two amplitudes should be equal. Right? Okay. Wavelength. Peak to peak distance. Now, that's the Greek letter lambda. The way I draw lambda is it's a candy cane that's like falling over. It's like leaning, right? Falling over. And so it sticks its leg out to catch it. Yeah, okay. So that's that symbol for wavelength. And what are the units of wavelength? It's a length, so it's got units of meters, right? Amplitude has units of meters just like I had before, okay? Frequency, it's the same, okay? But here's like sort of the equation that leads everybody astray, okay? And this is part of our toolbox for waves and wave mechanics, okay? It's this equation right here, okay? What are the units of frequency? Hertz, which is a inverse second. It's a 1 over a second, right? So if you take a wavelength in meters and you multiply it by a hertz, which is inverse second, what unit do you get? Meters per second. So this is a velocity, right? This equation can lead you astray. It can make you think that velocity depends on wavelength and frequency when it doesn't. If you know the frequency and wavelength of a wave, you can find its velocity. That's not a problem. The equation is true in that sense. But if we increase the frequency, if the frequency goes up, okay, gets bigger, then what happens to the wavelength? It goes down. And what does a smaller wavelength look like? Is it a spreading out or getting closer of the peaks? It's the closer, right? So frequency in a wave is like standing there and counting how many peaks per second go by. So high frequency's got a lot of peaks going by, which means their wavelengths need to be really short or small. A long wavelength, where the peaks are spread out, means it's going to be less crests or peaks coming through at the same time. So this equation right here is like one of the master equations for waves. You can calculate the velocity using it, and you should calculate the velocity using it, but it's really an equation about the relationship between wavelength and frequency. If wavelength goes up, frequency goes down, and velocity stays the same. What's the only way we can change the velocity of a wave? Change the material or the medium in which it is traveling. That's the only way we can do it. Okay? Changes in frequency and wavelength won't do that. Okay, it's time to talk about something that is a little bit embarrassing about my native language. What is this thing right here called? Yeah, okay. How do you spell trough? Oh my gosh. T-R-O-U-G-H. True is how you pronounce that word, right? Yeah. Right? No. Or trug? How do I know? Because everybody tries to put a U in my last name to make Balogh sound right, I guess. I don't know. Okay. How should you spell the word trough? T-R-O, I do a double F, just a trough, right? Okay. I'm not responsible for this word, but it's the opposite of a peak, right? It's the dip in a wave. So we got peaks, we have troughs. Wavelength can be measured peak to peak, but it can also be measured trough to trough. It's going to be the same. And we can even measure it equilibrium to equilibrium. You just have to skip one equilibrium in between, right? Because a full wavelength will have a peak and a trough in it somehow, right? Whether you're going peak, you start at a peak, come through a trough and get back to a peak, that's a full wavelength, okay? Whether you start with a trough and then get back to another trough, right? Or go the other way like this, doesn't matter. Those are all equivalent distances. We usually say peak to peak distance. You just kind of find the trough width or peak width if you want to, yeah. Half the wavelength. Yeah. But yeah, remember that the word trough is funny, and I'm sorry. Okay. One second. Yeah, okay. Other equations that we kind of need to have in our back pocket as we're working through waves. And then we'll kind of show you where they come from and how to use them, okay? This is the speed for a wave on a string. We will, this chapter, only do waves on like strings or in materials. Next chapter, we'll do waves in air. Or no, we're going to do waves in air right now? We might do waves right now. I can't remember. I always get a little bit confused between Physics 4C and Physics 2A, believe it or not, because we do waves and sound in both of them. And there's a slightly different order that we do them in, okay? But the speed of a wave on a string is equal to the square root of the tension in the string divided by the mass per unit length of the string. What just happened?
Somehow the coefficient of friction.
Yeah, it's not the coefficient of friction. We're at the point of physics where we really need to start recycling symbols because we've run out of letters of the alphabet. We're even running out of Greek letters, okay, right? This T right here, this is tension. It's not period. I'm sorry. This is probably where it's better to label tension as like F sub T or something like that, right? So you know it's the force of tension. This mu right here is the mass per unit length of the string. So like chain has really big mass per unit length, and twine or simple thread or something like that has very small mass per unit length. Literally, you can just take a meter of rope, get its mass, divide by a meter, you know its mass per unit length. So what happens to the speed of a wave the more tension you put into the medium? It gets faster. Does anybody here play a stringed instrument of any kind and have had to tune it, like a guitar, violin, something like that, right? When you change the pitch of your string to make it sound higher, what do? You tighten the string, okay? That increases the speed of the wave on the string. And why did the wave speed change? The material's properties changed. The tension in that guitar string went up, so its velocity changed. In that case, made the frequency change, okay? And the wavelength. What about this mass per unit length, guitar players or violin players? The low notes. Which kind of strings are those on your instrument? They're kind of thicker, right? They have more mass for the same length of string, and they sound a lower note, right? So the bigger your mass per unit length gets, the slower your speed will be, and hence the lower your frequencies will be in that string, right? So we're going to tie all of this together with musical instruments here, I think next chapter. This one is for the speed of a wave on a string. String under tension T, and string's mass per unit length mu. We'll actually use this equation in our lab, not the week we get back from spring break, but the week after, which is the same week we're taking an exam. Okay. There are 2 rules for spring break, okay? Number 1, have fun. Number 2, come back to me in one piece. Physically, mentally, emotionally, whatever, right? Okay? Come back to me in one piece. That's your assignment. Okay? There were I made a bunch of mistakes. Canvas made a bunch of mistakes when copying my course and didn't get the due dates right for a lot of assignments. This was discovered by several students. So I've updated a bunch of due dates, and none of them now should be over spring break except for this Saturday's homework. Is that true? Okay. Yeah. So but hopefully, because this Saturday's chapter 10, right? I know several of you already have it done. Boom, boom, boom. Okay? Get chapter 10 out of the way. Okay, what else do we got? We've got, I'm going to throw this one in right here, okay? Don't panic. I know. Too bad, Ella. All right, I'm actually going to write this as minus plus, okay? What these are right here are mathematical descriptions of a wave, and the sine cosine part kind of makes sense, doesn't it? Why would a wave look like a sine or cosine function? Because that's what it is, right? Okay. I mean, what did I draw up here? Sine function, right? I could have drawn the peak being at 0, right? Doesn't matter, right? But there are other symbols in here that are important for you to realize that stuff is going on, okay? First of all, what's A? Amplitude. Thankfully, that one stayed the same, right? Okay. But then we come up against K. Notice that a wave has 2 parts. It's got a spatial part with x attached to it, and it has a temporal part attached to it, the t. okay, with constants that sit in the front. This is literally a space-time equation, okay? So, K in this context is not the spring constant. I know, I'm sorry. Trying to drop this all on you at the same time. You'll feel mildly concussed, but we're gonna get through it, okay? K is something called the wave number, and it's 2 pi divided by the wavelength. Omega is omega. That one didn't change. You guys looked a little bit worried, okay? But omega is 2 pi times the frequency. I'll show you some examples of using this, but the minus plus thing we need to talk about. Do you see that symbol that says minus plus between the two? Okay. If minus, the wave peaks are moving to the right, traveling in the positive x direction. And if positive, they're moving to the left. I will not be held responsible for the nature of sine and cosine functions when it comes to kx minus and plus omega t. It just is the way it is. I would love for a positive sign to mean it's moving to the right, but that's not how it works, okay? If you see a wave function and it's got a minus sign between the two terms, which way do you know it's moving? To the right. And if there's a plus sign, moving to the left. Right? The number in front of the x, can you use it to find your wavelength? If k is equal to 3, can you find your wavelength? Yeah, because 3 equals 2 pi over lambda, solve for lambda, right? Okay. I think your textbook actually writes this out. I wouldn't write this down if I were you. Your textbook says y equals a sine or cosine, and then they'll do 2 pi x over lambda minus plus 2 pi ft. Yeah, what did they do there?
Made it complicated.
They just put the definitions in and scared you more, right? Because there's just more stuff in there, right? So your book might do it that way. Most often, it will be written like this: websites, AIs, all that kind of stuff, right? T is time. The little t is time. Okay. The key thing here is that you got to realize in some of these equations, it's not period, it's tension. It's not friction, it's mass per unit length. It's not spring constant, it's wave number. Right? How do you know? How do you know, say for example, that you are dealing with a wave number versus, say, a spring constant? They're both using K. How do you know which is which? Context. In what context is the equation being applied? This one can only be applied where? Springs, right? So if there's a spring in your problem, do you have a wave number? No, you have a spring constant, right? But if we're talking about waves, are there any springs in waves? No. No. Okay? So it must be, especially when it's next to this x, right? This is not a force, right? Okay? This is a wave number times a position. Okay? This function is the plot. It's how you get the plots of the waves traveling through space. All right, there's probably something else I forgot. I might have to come back to this screen, but we will go and just try some things here, right? Can we work our way just through the concepts of waves and what's going on, okay? So what do we got here, okay? Got a wave, it's good, okay? They want the function that describes this wave, okay? The function that describes this wave has a pattern. Amplitude, sine or cosine, kx minus plus omega t, and we need to fill in the blanks. Okay? Do we know what the amplitude is? 0.6 meters. Okay? Do we know what the wave number is?
2.5?
Nope. It says the wavelength is 2.5. So lambda is 2.5. Let's identify the other things we have. So we have 2.5, we got the 0.6. The other number we have is period. Uh-oh. Capital T. Right? 1.5 seconds. How do I know this capital T is not a tension? It's in units of seconds, right? If it were a tension, what unit would it have? Newtons. Why have I been on your case? And some of you, why have I taken 1 point off on an exam where the problem is correct, but you didn't put a unit down? Because units are important, right? They tell you exactly what's going on. Okay, so we need, to be able to write this function down, we need the three things that aren't variables in the equation. X is a variable, t is a variable. They'll change. We can just put whatever numbers we want in for that to find out what's going on. But we need to be able to write down this function. So we have the amplitude. That one's done, right? Okay. So how are we going to find the wave number?
Cry.
2 pi over lambda, right? This is 2 pi. I'm going to be fancy now. 2 halves is 5 halves. So this is 4 pi over 5. Interestingly enough, what are the units here? Not that it matters that much. It's inverse meters, yeah. It's just inverse meters. All right? You won't need it for reasons I'll show you in a second. Okay, what about omega? Can we find omega? Yeah, remember from our relationships from last chapter? Omega is equal to 2 pi divided by the period. So this is 2 pi divided by 3 halves, which is 4 pi over 3. And what are the units of omega? It's a radian per second. That one's we don't say radian per meter for the wave number, but we do say radians per second for omega, because a per second is a frequency, isn't it? Linear frequency f. So we're trying to disambiguate between those two units. Big fancy word for tell the difference. Okay, so now that I have all these numbers, I can chuck them in, right? This is going to be 0.6 sine or cosine. I'm not going to worry you guys over picking the right one. K, 4 pi over 5, x, that's the variable. Ooh, plus or minus? How do you know it's minus? It's going to the right. Okay, so kx minus 4 pi over 3t, and then you say in SI units. And when you say in SI units, what does that mean? What's the 0.6 in? Meters, right? And you can then use 4 pi over 5 to find the wavelength in meters. And you can use the omega to find the frequency in hertz, inverse seconds, right? So that's what SI units means, right? It means that you will get the appropriate SI unit out for anything that you pull out of the function, okay? So that's how you write down the mathematical description of a wave, just knowing some stuff about it, okay? We can also reverse this. This is how they find wave functions in the first place. You map the wave, you put it into a computer, you have the computer fit to sine and cosine functions, and it'll spit out a function. Once you know the function, you can find anything you want about the wave. Notice how this one was written to specify, just to be very clear, that y is a function of x and t. X and t are the variables here, right? Okay, they want to know the speed, wavelength, and frequency of a wave. What do we know about this wave? Let's write down what we know. There were no numbers given in the words. All the numbers are in the function.
It's going left.
Ah! Because of the plus sign, right? Okay. All right, what else do we know? Ooh, we know the amplitude. What's the amplitude? 10 what? Meters. They didn't say in SI units. They were bad. Usually if there's no unit specified, you assume SI units. Okay. What's sitting in front of the x? Good job, 2 pi over 3. But it's the wave number, right? K. And then what's sitting in front of the t? It's omega, which is pi over 6. All right. So, speed. What's the speed? It's wavelength times frequency, isn't it? So we got to find both the wavelength and the frequency. How are we going to find the wavelength? How are we going to find the wavelength? Why is it called the wave number? Because it can be found. It can excuse me. It can find the wavelength. Oops. So if we set 2 pi over 3 equal to k, which is 2 pi over the wavelength, then I get a wavelength of 3. How did I do that? Algebra. 3 watts? Meters. So there's the wavelength. That's one of the things they wanted. Now I need to find frequency. What is frequency? Where is it hiding? In omega. So 2 pi f is what omega is equal to, right? Pi's cancel. This looks like a frequency of 1/12 of a hertz. 1/12 hertz, right? Okay, so we know the frequency. And how are we going to find the speed now? Just multiply them together, right? The wavelength is 3 meters. Frequency is 1/12 hertz, which is a 1 over a second. 3 divided by 12 is 1/4. Job done. We should throw in back here on this screen. We know that wavelength is equal to 2 pi divided by the wave number. That's just a rearrangement of that equation. And we also know that frequency is equal to omega over 2 pi. So what's speed going to be? Another way of writing speed. It's wavelength, but what's the wavelength? 2 pi over k. And its frequency, what's another way to write frequency? Omega over 2 pi. What happens to the 2 pi's? They cancel, right? So another way to get this speed is omega over k. It's the same thing, yeah.
I was going to ask, what does k represent again?
It's just the wave number. It's 2 pi divided by the wavelength. A lot of math you really don't want to know that gives rise to that. Could we have used a better symbol?
Yes. We can use the Among Us symbol.
No. Yeah, we'd have to reach into like Chinese or something to get better symbols, which I'm all for. Their language is based on ideograms, which means they have basically an infinite number of characters. All right. All right. I need a volunteer. I just need somebody to hold the end of a spring for me. Drew, you always volunteer. Come on up. I appreciate it. Okay, don't let go. Okay, but hold on. The slinky of all slinkies here, right? Okay, hold it up, kind of up high. All right, there we go, okay? So what I'm going to do is I'm going to put, not a wave, I'm going to put a wave pulse on this spring, okay? Hold on. Right? Do you see how that pulse travels up and down? This is a transverse pulse, okay? The direction it's traveling is horizontal along the spring, right? Okay? but the way that the way that the pulse is happening, right, is vertically. Okay? I can also lay it on the ground. Calm down, now lift up slowly. All right? I can also, hold on, you ready? Right? Do you see how that pulse is traveling up and down the spring, right? But it's a transverse pulse. The pulse is perpendicular to the direction that the wave is traveling, right? Okay? All right, let's put it on the ground. Let's get it steadied, and then up slowly. Okay? I am now going to put a transverse pulse. It's actually already there. Oh, it turned into longitudinal pulse. It turned into a transverse one. Let's try it again. Do you see what's traveling down the spring? It's not so much going up or down. It's a compression that's traveling along the spring, especially as it gets lower. Do you see that compression bouncing back and forth there? Right? Okay. Put it on the ground. And let go. Thank you. What's that? No. It has everything to do with the two different ways that waves can travel in materials. There's actually more than this, but these are the two big ones that we're going to deal with. Transverse, where the wave peaks and troughs are up and down, but the wave is traveling sideways. There's this perpendicular disturbance to the direction the wave is traveling. And all the examples and drawings we've done up to this point, I've showed you a transverse wave. And then there's longitudinal waves, which are a little bit harder to visualize and draw because they're all about a compression that travels. See how this compressed region is moving along? And then there's a stretched out region that's right behind it. It's a series of compressions and stretches. There's a word, it's not common, but it's the scientific word for this. So I'm going to introduce you to it in case it comes up in your studies. There's compressions, that's where it's squeezing together. The opposite of a compression is a rarefaction. R-A-R-E-F-A-C-T-I-O-N. Rarefaction. So compression, squeezing together, and a rarefaction is a pulling apart. Okay? You can say it stretches out. That's easier. But there is a technical term, and I've watched AIs and books and other things kind of drop that thing. So I already gave you the speed of waves on a string. Remember that one? Okay? Where the speed was equal to the square root of the tension in the string divided by the mass per unit length. But what about in air? Because we want to start talking about sound waves. What does the speed of a wave depend on? The material, the medium in which the wave is traveling. What's the medium of sound waves? Air. What affects the properties of air? Temperature, density. It's actually density that really affects it, okay? But density can be changed with temperature and with atmospheric pressure and what's actually in the air, like what kinds of gases you have in the air, which again, all kind of comes back to play havoc with the density. I don't think this equation's in your book, but it's a really handy equation to have because it approximates the speed of sound with temperature. I think your book's equation is a lot harder. They get into stuff like molar weight of a gas, and it's just too much, okay? You actually don't need to know any of that. The speed of sound in air is 331 meters per second times the square root. You guys promise not to kill me? No? I'm not going to get, yeah, just watch. Be careful. Okay, all right. T divided by 273 Kelvin. That T is temperature. I don't make this stuff up. What?
Do we need the .15 on the Kelvin?
No. I mean, you can if you want, but no. Okay? So this T is temperature of the air in Kelvin. I know we haven't done thermodynamics yet, but you can convert between Kelvin and Celsius and Fahrenheit with a phone, right? We'll get into the conversions later, but just realize you need to know the air temperature in Kelvin, not just Celsius. Temperature in Celsius is the temperature in Kelvin plus 273.15 degrees. So there's your conversion between Celsius and Kelvin. Between Celsius and Fahrenheit, good luck.
Is that backwards?
Yes? Did I say it backwards too? It must be because it was in my head that way. Yes, thank you. That it is now forwards. So you got to add 273 to your Celsius temperature in order to get the Kelvin temperature. Okay. Difference between Celsius and Kelvin is what? I mean 273.15. But like, what's the difference? One of them puts 0 in the correct spot. Kelvin puts it at absolute 0, the coldest temperature that can ever be achieved in nature. That's the difference. Anyway, if it's freezing, if the air is freezing 0 degrees Celsius, how fast is the air going? How fast are sound waves in air going? 331 meters per second. Okay? If it's room temperature, so here's the big takeaway. Okay? We are going to approximate the speed of sound as 300, oh darn it. Which one do I use all the time? 343. If you're not told what the speed of sound in air is, just assume it's 343. You'll be fine. Okay? That's sort of the standard room temperature, pressure at sea level number for the speed of sound. Some books will say 340 instead of 343. They'll like just drop a significant digit because it's actually pretty close, right? The point is, speed of a wave depends on the medium, the material in which it travels, and if the material properties change, the speed changes, and you can get all kinds of interesting effects. So let's talk about sound waves. Sound waves are longitudinal waves, and we know this because longitudinal waves can exist in any material. There's different kinds of phases of materials. What's 3 of them? Solid, liquid, gas. Okay, there's more. We'll get to that later. So transverse waves can travel in solids only. Transverse waves cannot travel in fluids. And in physics, a fluid is a liquid or a gas. They're both lumped as they're just fluids. Okay? The difference between a gas and a liquid is that a liquid will sink to the bottom of its container, and a gas just takes up the full volume. So longitudinal waves can travel in all the different phases of materials. They are not limited. Transverse waves can only travel in solids. It has to do with how the atoms are connected and the restoring forces in those materials. Air is a what? It's a gas, a fluid. Therefore, the sound waves that are traveling through it are longitudinal. When I speak, right, and you hear the incredible dulcet tones of my voice, right? They come out of my face, right? And they travel to you as a series of compressions, right? And then you have this architecture in your head on the side. Oh, by the way, in case you ever needed to know the speed of sound in carbon tetrachloride, there it is. I don't know why would I want to know the speed of sound in lucite? The whole point is the speed of sound is different in different materials because the speed of a wave depends on the material in which it travels, okay? So let's talk about how we're going to think about all of this, right? We're going to develop a conceptual model. This is a lie, but it's a good one because it simplifies our understanding of what's going on without having to get into the nitty-gritty details. Don't worry, other people have done the nitty-gritty details for us, and those people still use this model. We're going to approximate sound waves as these like rays. Don't panic, these are not vectors. Okay? They're just arrows that are indicating the direction that a sound wave is traveling. If the sound is a point source, and we'll just assume every sound is just coming from a single source, then the sound waves are emanating from that source and spreading out as like spherical waves. And every like wave front, every peak of this wave, every compression that's coming at you is one of these like nested spheres of sound that's coming at you. So sound propagates spherically outwards from its source. And when we take this ray, this arrow, and we just draw it, right, in the direction of propagation. So how many rays should we draw? I mean, how many rays could there be? An infinite number, right? They're going out in all directions from a source. We generally just, if we're going to picture like what's going on here, we don't like draw wiggly things traveling places. We just draw an arrow, right? Say, this is a wave, it's going that direction, right? The arrow is pointing in the same direction as the velocity of the wave. But again, don't worry, it's not a vector this time. It's just a graphical way to handle. So like sound just sort of spreads out and the rays spread out from each other. So this is kind of the conceptual model that we're going to be dealing with, right? The question that I have, right, is what the heck is going on with all of these parts? There's something that is absolutely incredible to me, right, about how we and other organisms are able to communicate and present meaning and doing all this kind of stuff. And I'm not even really going to get into like the philosophical ramifications of language, right? I just want to talk about the physics of what's going on here, right? Let's start on my end. What am I doing? I'm talking, right? Okay. I am changing the tension in the muscles of my throat that are connected to these vocal cords, right? These two ligaments, not really ligaments, they're just sort of fleshy bits that are in your throat, right? And they will cause the air pressure in my lungs to increase and then explode out, and then increase and then release, and then increase and release. And they'll flap back and forth at certain frequencies that I then take and shape with the shape, all the holes that are inside my head. And then I project them out into the classroom, right? This is not the way I talk to people one-on-one. Like if I'm talking to you, hey, how you doing? Right? I'm not shouting, right, at your face, right? I've got to be able to project out into the room. And I do that projection by like doing tricks with my diaphragm and getting it out. It's very similar to what a singer might do to kind of support the sound that's coming out. Those sounds, having come from these flappy bits inside of my throat and then being shaped, right, by the holes in my head, emanate out in that spherical pattern that we talked about. And they're coming at you as these waves of compression, right, coming at you, and they have to be collected somehow.
So when I hear a singer and they're hitting like a certain note, like Mariah Carey's hitting a high note and it's consistent.
I'm not Mariah Carey. I was going to try it, but no.
Yeah. But when they hit that high note,
It's like my highest note.
but is that just going to be one consistent wave of non-digressing levels? Just going to be the same?
In the simplified version, yes. Now, Mariah Carey's voice has a lot better quality than mine, so she's going to have a different kind of waveform. We're going to get into that when we start talking about instruments and things like that, but it'll be similar, right? Like, my voice can go as low as and as high as right? That wasn't even really falsetto. That's just the natural range of the muscles in my throat. And so people that train in this will learn to support, right? And do a sort of a different, I can't even really hit a falsetto. I didn't even make it, right? So There's different ways to pull it off. But what the heck are these flappy bits doing on the side of your head? You actually don't need these. I didn't know. You can hear without these. Let's do an experiment, okay? What I want you to do is I want to take your hands and I want you to cup them behind your ears, like kind of maybe fold the little flappy bits, which actually aren't your ears, fold them a little bit forward, but like make sure that your hands are making your surface area bigger. And then listen to the sound of my voice as I attempt to keep up a monologue up here with one breath in my lungs. Can you hear any difference between not having your hands on your ears and having your hands on your ears? Is there any difference in the quality of sound or the loudness of the sound as I keep my voice doing exactly the same thing and you take your hands on and off your ears? Did anybody notice the difference? Yeah. What happened when you put your hands behind your ears? It sounded louder? Did it sound brighter?
I said flatter.
Flatter? It's not flatter. Yeah, okay, now, same experiment but different. I will keep up the same monologue, but now I want you to take your ears and I want you to pin them back to the sides of your head and kind of flatten them out and then let them go. And see if you can't tell the difference in the quality of the sound as you go from them flat to not being flat, flat to not being flat, flat to not being flat, right? Did you hear it? No? Next time you hear like at a concert or some constant source of noise, try like pinching, maybe not near people, but pinch your ears, right? Okay? Like that, back to your head. Versus like this. You'll be able to hear better with your hands behind your ears than if they're pinched like this. But in both cases, you were able to hear the sounds. So what are the flappy bits for? It's trying to take the noise that's out there and run it into your head. Because your ear actually exists on the inside of your head. Now this might be where this is where we need Miss B. She can come and tell me all the anatomy and physiology and get it correct. What are these called? Pinnae?
Yes.
Right? Okay, flappy bits. Right? Inside your ear, you have an eardrum. Okay? It's a flap of skin, okay, that's sitting there. And what does it do? Doesn't filter. It collects. Everything that's funneled into your ear, every sound wave, every Q-tip, every finger, every pea, whatever it is you are sticking in your ear, is going to the eardrum, which is why you should never put anything in your ear. Does anybody here know what the American Medical Association recommendation for the size of object that should be put in the ear canal? I'm not kidding here. This is in the literature and in the diagnostic manual. The smallest object that should be put in the human ear by not a doctor, by anybody else that's not a doctor, is what? Your elbow. That's how they define it. This is the smallest thing that should go in your ear. You know what I thought when I read that? I thought there's a bunch of people that are... Right? What's the point? Don't put anything in your ear. Okay. Because the eardrum can get damaged really fast and it's very painful. What's the eardrum doing? As these waves come from my mouth, compression waves coming at you, your flappy bits collect it, channel it into the ear canal, and then they run up against the eardrum. What's it doing? It starts to wiggle back and forth at exactly the same frequency as the sound that left my throat. But that is a very tiny wiggle, believe it or not. And so we've evolved a system of natural mechanical amplifiers with 3 of the bones in our ears, the hammer, the anvil, and the stirrup. Yeah, all those fancy Latin names, okay? I dropped out anatomy and physiology right away, okay? These bones are a natural amplifier. They have like hinges on them and stuff that allow the signal to get louder. And that signal is then routed to the snail that lives in your head. The cochlea, okay? Cochlea is filled with fluid. The semicircular canals are up there. They are like a 3-dimensional, 3 degrees of freedom sensor in your head that tells you, like the fluid in there will tell you where your head's going. But more importantly, the fluid that's in the cochlea is there to take the mechanical vibrations of the eardrum, amplified by the bones of the ear, put into that fluid. So now we've got waves traveling in a fluid, and in that fluid are suspended little tiny cilia, little tiny hairs that line the walls of the cochlea. And each of the base of those little hairs is connected to a nerve ending. And the cilia will react to the specific frequencies that they're tuned to. And when they do that, when they go, oh, wave, your brain, they send a signal, an electrical signal to your brain, and your brain goes, ah, noise. Why does it take so long for a kid to learn how to talk? They're not dumb. Okay? Language isn't just the noise, is it? It's the pattern of noises that are being made to make up the words, to then have what is quite frankly a very awkward way of communicating what's going on in my head to your head, right? So it takes a while, like for some of us it's still happening, right? It takes a while to really get down what the sounds mean. Vowel sounds, consonant sounds, all that kind of stuff. Interestingly enough, though, adults help out with this in ways that they aren't aware of. What happens if you give an adult a baby? Here, hold this baby. I'm talking about raising, I'm not talking about having children. I'm talking about just you give an infant to an adult, what happens? They turn into an idiot. They do, right? Because they'll take the baby, oh, what just happened? This is cross-cultural, by the way, right? Different cultural norms have different ways to respond to things, but across cultures, you give a human adult a human infant, and they will start talking nonsense to this infant. Why?
Infant telepathy.
Feels right, doesn't it? Genetically, we are programmed to help our young survive. One of the survival things that we benefited from, that really separates humans from the other animals, is this ability to communicate very precisely. How is an infant supposed to know what sound sounds like? When adults are talking to each other, how do they talk? Hey man, fist my bump, right? That's not how it's said. Quoting a movie there and a book, okay? Not the same thing, right? You talk, but we generally as adults talk in a monotone to each other. Hey, how's it going? You doing okay? Yeah, oh, I'm really sorry about that. Do you notice how in that conversation you really don't change the frequency? You don't go, hey man, how's it going? You don't do that. You do that to kids, but you don't do that to adults. Why? Because you want to have friends, and nobody's going to be your friend if you are talking at them like that, right? If you're talking at them like a baby, they'll be like, right? As we grow older, we learn the sounds, and then we use the sounds that give precision in our communication. Prior to that, we're helping the young sort of program their brains and hear all these different sounds, different ranges of frequency, and all of that kind of stuff. It really is an incredible system that works pretty darn well until it doesn't. There's a lot of stuff that can go wrong in this system that can lead to hearing difficulty or hearing loss. at the risk of sounding exactly like what I am, an old white dad, please listen to music quietly in your earbuds. No more than 60% of the total volume slider should be used. Why? Over the ear or earbuds, it doesn't matter, but over 60% on the volume slider from a phone or a device or laptop, you are getting into the territory where you can cause permanent damage later in life to your hearing. Those little cilia I was talking about, they can get overstressed. What happens when you get overstressed? Life falls apart, right? What happens when a cilia gets overstressed? It just stops. And you lose the ability to hear certain sounds if you've overstressed. Please listen to your music. Please go into that zone of silence that everybody can ignore me and I don't have to have social interactions. Do it, right? Just don't do it so loud that you were causing damage.
How does listening to music with noise canceling work?
We're going to talk about noise canceling later. Okay, because we got to talk about interference and sound waves and things like that. But the short version of your answer is the earbuds are inverting the wave and adding them together to cancel out the noise that you don't want and only let the noise through that you have. People with hearing loss, again, variety of reasons for this, but one of the more correctable problems has to do with this cochlea, this brain and ear interface, like the physical outside world going into your brain. And so there can be this thing called a cochlear implant. It looks a little bit like a hearing aid, and technically it is. It's got a microphone in the part that's worn on the ear. But then there will be, you can tell a cochlear implant from a standard hearing aid because there'll be like a spot on their head where the implant will attach. It's actually a magnet. They can just take this thing off. Okay, and they can put it back on and the magnet will seat it. What you got on the head is a transducer. It's just, it sends an electrical signal. And that transducer is wired into their cochlear implant. The cochlear implant gets inserted inside the snail and tries to overcome difficulties that they might have with getting the nerve impulses into the right places at the right time. Okay? This can restore complete hearing loss, depending on whether or not the hearing loss is of a certain type. I want to play a clip for you. This is a video of a young woman who is getting her cochlear implant for the first time, turned on for the first time. Let's go to this, and then here. Okay, so the story behind this one, so we've got the nurse, the technician that's getting the implant fitted correctly, right? She's already had the operation for the insertion that goes into the ear. She's got the transducer. They're for the first time getting like the transducer and her hearing aid all set up. She had lost her hearing around middle school, degenerative defect. That caused problems with her cochlea, but they were able to determine that they could fix her hearing. This will be the first time that she will hear sound since middle school.
It's like so clever.
So they're trying to get the transducer in the right spot.
So now technically your device is on. Can you tell? Oh, that's exciting. Here, you can put it down for a second. Just get used to the sound. What does it sound like?
She had never heard her husband's voice until this day. We live in Star Trek. Like seriously, right? That we have these technologies that can restore sound to the deaf, right? We actually have technologies, you'll learn about it in Physics 2B maybe. People who are blind are starting to see again. It's crazy, right? It's just nutso that we're able to pull these kinds of things off. There was a wonderful article I read like more than 20 years ago. And the article was called My Bionic Pursuit of Bolero. It was a story written by a deaf person who had gotten a cochlear implant like back in the 80s. And the very first ones were very rudimentary. They were like, they could basically like isolate 1 or 2 frequencies. And so they heard things, but everybody's voice sounded kind of like a robot, right? That old-fashioned robotic voice, right, is kind of what people heard with these. And he documented over the course of 20 years the improvements that were made in the technology by listening to a piece of music called Bolero. Bolero is a classical piece of music that happens to use every single instrument of the orchestra at different times in the musical piece. It's exactly the same melody over and over and over again, but through different sections of the orchestra. It's actually a eerily mesmerizing piece when you sit down to listen to it. And it's got like a drummer that is like totally zen. Anyway, this article writer documented the improvements in cochlear implants going from basically hearing robots and not being able to hear music at all to within 20 years being able to hear every single note in the orchestra. Like, why are we bombing each other? Seriously, when we can do stuff like this. It is absolutely nuts. Let's go back. Okay, so that was a little bit of a digression, but I know some of you are going into medical fields, and I just wanted you to, we wanted to tie it into something that really just kind of impacts people on a big level. We're going to get through part of this. I'm going to start it now, and then we're going to have spring break, and we're going to forget everything. We're going to come back, and I'm going to remind you of everything you've forgotten. Yeah, but let's just get started on this so that you can see it twice, right? What we're going to do now is we're going to talk about how you measure how loud a sound is. We use a scale called decibels, which is the problem. But let's back up just a little bit and talk about intensity. Intensity has a definition, okay? This is not moment of inertia. Told you, we're recycling symbols now, right? Okay? It's power divided by area. Sound is produced by whatever, speaker, throats, whatever, okay? At a given power. And this is energy per time. This is power in watts. And we've studied power before, okay? So the power of a sound really doesn't change other than, like, I can make my voice really soft. Or I can make it really loud. That's me adjusting power. Intensity is what happens to that power with distance. How you guys doing back there? Nosebleed section. Can you hear me okay? Yeah, you like sitting there so you can ignore me? Back of the bus is great, isn't it? Okay. Up here in the front, people are going deaf, right? Because I'm trying to project into the room so that people all distances away can hear what I'm saying. It's how we humans communicate. So I set a given power with my voice, but the loudness of that sound falls off with distance. This is what intensity is.
Does intensity also have to, does it correlate with the density of the air or?
No. Yeah, okay. There's something called attenuation, which we don't get into, which is like the bouncing of sound off things and reverb and a bunch of other things. But yeah, for our purposes, no. Yeah, power is power. The same power at the back of the room as the front of the room. But the reason the people in the back of the room hear a quieter sound than the ones in the front do has to do with intensity. Remember how I told you that we model sound as this spherical wave coming off of a point source? Take the power and spread it onto the surface area of one of those spheres. And what happens to the surface area of that sphere as you get further and further away from the source? It gets bigger and bigger and bigger, which is why we are going to use power divided by 4 pi r squared for sound. Intensity is power divided by area. You want high intensity? Get high power over a tiny area. You will have lots of intensity. So this works for light, works for sound, works for anything. Okay? But for sound, we're going to use power divided by the surface area of a sphere, which is 4 pi r squared. So notice what happens to the intensity as we get distance from the source, right? For somebody that's sitting just 1 meter in front of me, there'd be a certain intensity, okay? But for a person that's sitting twice as far away, person in the front row here's 1 intensity. What is somebody that is twice as far away, 2r away? Not half, it's r squared. Yeah, so intensity 1 might be p over 4r squared, but intensity 2 is 4 pi twice the distance that we had before. You square the r, you get r squared, right? But you end up with this factor of 4 floating around times the original amount. What if it's 3 times as far? People in the third row.
12.
It's 1/9. Fourth row? 1/16. Last row? 1/25, right? That's how the intensity is falling off, right? Throughout this room. And so to keep that sound like even, right? So that people in the back can hear it and people in the front aren't completely overwhelmed by my presence. We've evolved a hearing system that can tackle those very large ranges of sound.
Can you label which formulas these are applied to?
What do you mean?
Like I over PA, is the 1 over just a more explained version of it? Or are these 2 different formulas?
The same formula. I just stuck in twice the distance to show you that you get a power.
I'm referring to the I equals P over A and I
Yeah.
equals 4 pi r squared.
The same equation. Yeah, it's just one I've substituted the area of a sphere into, right? What's the faintest sound that a human can hear?
A whisper?
Nope. A water drop, you said? That's actually too loud.
A dying breath?
Oh, geez, going dark now. The threshold of sensation, the intensity at which our ears can first hear a quiet sound, is 1 times 10 to the minus 12 watts per square meter. I asked an acoustical physicist once, what is that? Like literally, what is that intensity? And they said, we actually have a kind of a definition for it. Imagine you are alone in the woods. I was like, I've heard this joke before. Okay. Okay, you know, the psychological thing is like if a tree falls in the woods and there's nobody around, right? Is there still a sound? The answer is yes. Sound is vibration, so there's going to be vibration. So I don't like philosophy or psychology. Anyway,
That's why you picked physics.
my wife changes the joke because her joke is, if there's a man alone in the forest and there's no women around, is he still wrong? Unfortunately, the answer is probably yes, in my case a lot. Imagine you're in a forest, you're alone, there's no beeps and boops from your cell phone, and there's like no wind. And a leaf like falls off of a tree, floats to the ground, and lands on the forest floor. The sound of that leaf hitting the forest floor is about 1 times 10 to the minus 12 watts per square meter. No other wind, No other sounds. No bears are chasing you. Nobody's talking at you. Okay? It's just that leaf hitting the ground. That's the threshold, human threshold of intensity. Is there an opposite end? Is there a sound that is so loud you can't hear it?
Maybe like a high enough frequency.
There's a high enough, well, frequency doesn't have anything to do with this. We're talking about just the power and intensity of the sound. There's no threshold where you stop hearing, but there is the threshold of pain. You have to say it that way, the threshold of pain. That's 1 watt per square meter. What is the difference between when we barely hear something to when we go, ow, that hurts? What's the range? 1 trillion times difference. 10 to the 12 is a trillion, right? So from the threshold of pain to the threshold of hearing is 1 trillionth of a difference. We have the ability to hear a very large range of intensities. And dealing with big or small powers of 10, right, becomes really cumbersome. Which is why when we get back together after spring break, I'm going to introduce you to the decibel scale. Spoiler alert, you're not going to like it. Because it's going to involve logarithms. But you don't have to do it until after spring break. Have a fantastic spring break. Like I said, have fun, but come back to me in one piece. Right? I'll see you on the other side.